if we are on an open set, we want to define what it means if I'm on a more general retract. Okay, so let's start with a strong local bundle. So I may assume that I may assume that 0 lies in this thing here. So now I'm interested in a section. So F is there's the infinity section defined near 0. And now comes the important definition. So if near 0, so it's some kind of a germ like this. So then F0 possesses a filling if there exists a germ. So when I constructed this O here, I started with this thing here, and I then also have this bundle over F, and then I had this strong bundle retraction. Yeah. Over U, and the underlying R from U to U, and this O is R of U. Yeah. So there exists a germ G0, and of this thing, yeah, so of this thing defined on this relative open set, so that the following holds. So f of x is equals g of x for x in O near 0. So if I restrict this g, which is defined on that open set here near 0, if I restrict it to the O, then f and g coincide. So g is an extension of this f. Secondly, let me write, suppose R of UH is R of U rho of UH. If G of Y equals rho of Y times G of Y. So what this means is for for a point y in U near 0, then y is in O. So what is this condition here? This condition is precisely the defining condition for the fiber of K. So if your G, which is defined on a larger set, has actually the image in K, you can conclude that the original point was already in O.
What was K?
K? Oh, K is your local bundle. So technically, this lies in U, and this thing here lies in U plus F. So now, so the G goes into, so the G would be defined on U, on a neighbor of 0 in U, and would take image, would be a section. So if I take the principal part, would lie in F. So so this G is an extension, which is this condition of F. So O is a possibly very small set containing 0. You have G defined near 0. It would extend that map. Then, what does this condition mean? This is precisely the defining condition for the fibers. It means if this extension has a property that it lies actually in the fiber of that bundle, then the underlying point had to be in O, in the retract. And 3.
When you say SC factor, is that the same as SC?
Yes, yes. And then the linearization. So what this says is I have an extension, and as long as the solution, so for example, if G of y is 0, then in particular it satisfies this condition. So I can conclude y is in O. If y is in O, it's the F. So f of y is 0. So that means condition 1 and 2 already imply if I solve the equation g of y equal to 0, then I have a solution for f of y equals 0, if y is close to 0. But so it means I added conditions to my original problem which don't create additional solutions. But I want to also do it on the linear level that it has also in some sense the same Fredholm index in the original. So the linearization of the map y goes to identity minus rho of y. I should write, I think here I have actually write r of y. Yes, if this is true, I should write r of y. And here, so the linearization of the map at 0 is an isomorphism. From the kernel of dr of 0. So the kernel of identity minus dr of 0 is the tangent space of O at 0, and this is a complement of the tangent space in E. So this is a complement of the tangent space of the original problem, and this to kernel of rho of 0 is an isomorphism. So what it means is I extended the problem in such a way that I get the same solutions as before, but by starting on the whole set. Now, so what I will require now to be a Fredholm section of an abstract bundle is that in local coordinates I can turn it into something which can be filled, and the filled thing is a Fredholm germ, as I defined it before. Then you just always do the implicit function theorem for the filled version, but you know it's actually a solution in your after change of coordinates in your manifold. So then the only question you can ask is, okay, you can always require forcefully that something like this happens, but doesn't happen. Does it actually have applications? And in fact, it turns out that in applications, these fillings are just obvious. Once you see one example, you see the fillers all over the place. So, for example, if you study, suppose you have 3 points, and you study on the space of possibly broken trajectories this operator here, the gradient flow equation, the gradient flow operator. Then the neighborhood of this point here, the neighborhood of a broken trajectory, could only be modeled in this world of retracts. So one would be interested, what is the filling near a broken trajectory? So if this here is the point A, the point B, the point C, it turns out that the filling, so we would be dealing with a pair of broken trajectories here. And after a suitable, so there is a change. So okay, so now I have to say something which I never wanted to say. So okay, so how do I get out of this without writing too much? Okay, so there's a change of coordinates which leads to, let me write it like this. So out of 2 passes, I construct something like this. And what is this? This here is an unbroken pass. So this is a pass from A to B. This is a pass from B to C. This is a pass from A to C. And this here is a pass from R into the tangent space at the point B. So if I have a broken path, I can in some sense sew this together to get a path directly going from here. And then there are sort of these tail ends, and the tail ends are collected here and are interpreted as going to the tangent space at the point.
No, the angle between them.
No, there's no angle.
Something like
No, it's a tail. No. If you glue this together, then there's sort of this. There are some tail ends here. I mean, you have to sort of, at some point, you have to make a transition from here to here. So what you forget is this part, and you just combine this in some way here. So then, on this level here, you have this operator. So you have the operator for the path going directly. So this would be for, let's call this U and V. And for this part, the operator would be V goes to V dot minus basically the Hessian. Let me write phi double prime at the point B applied to V. Yeah, so there is a change of coordinates that the filled version here in the neighborhood of this thing is the same like describing that stuff here on some other things together with this linear operator here. That would be the filled version. That would be the filler. So, and this is always the same. Like if you do Floer theory, in Floer theory, you would have operators around periodic orbits that would appear then there if you do Floer theory. If you do Gromov-Witten theory and glue 2 spheres together, the operator is here, in fact, the Cauchy-Riemann operator on the linear Cauchy-Riemann operator on a sphere with image Eckner maps which go in the tangent space at the symplectic manifold at that nodal image, together with the condition that the values on the north and the south pole are antipodal. That's a space of functions.
Could you be more explicit? I didn't follow what you said.
Yes. So.
So over here.
Okay. So the abstract thing is, I I would start with something which is, start with an f, but it's defined on the strange spaces. And I want to define, which I haven't done yet, I want to define what a Fredholm problem is in the general case. So the first thing which I have to introduce is the notion of a filler. A filler is something, if I'm working in local coordinates, so I start my f is a section of this strong bundle. A filler is an extension to an open set. That's this property, which however has the additional property that if the image of this extended thing lies in K, in a fiber of this bundle, then this has to be the image point of a point of my retract. And then in some sense what I added to it, so I have something defined on O, then I extended it to an open set, so I have some kind of a normal direction. If I linearize in the normal direction, I get an isomorphism between two spaces. I get an isomorphism between a complement of the tangent space of O at 0 and to the complementary fiber, which I had to add to K. So it's sort of, in some sense, the best possible extension. I have extended, it's like a stabilization in some sense. I added isomorphisms to the problem, linear isomorphisms, more or less. I mean, that would be the ideal way, but it hasn't to be linear. Yeah. So now in this case,
I was just going to say, if you already have these plus and minus maps at least drawn on the board, would it be helpful to actually state what R and rho are and what F is?
in this case.
Yeah.
Yes. Okay. So let me describe here what the local situation is in practice. So let me assume that my point B is 0. Now, of course, I don't care where things come from. I just explain to you what happens here. So this would be something defined on a half line. This would be something defined on a half line. So the input space, say, would be let's call this U and V. So this is U and this is V. Yeah, they both go to 0. So now let me fix a number tau. So let me fix the number R here for the moment. And then I construct an isomorphism to H2 of 0R cross Rn cross R2 of Rn as follows. This element here I call plus R uv of s is so. Now what I'm taking is a cutoff function beta, which looks like this. Is beta of s minus r half u of s plus 1 minus beta of s minus r half v of s minus r. And minus of r of uv of s is minus 1 minus beta of s minus half u of s plus beta of s minus r half v of s minus r. So what you observe here, this is a 2 by 2 matrix of the form beta 1 minus beta minus 1 minus beta beta, so the determinant is positive. So this thing is defined. So remember, v was only defined on r minus. So if s exceeds r, it wouldn't be defined. So s has to be less or equal to r. The u is defined from 0 for s greater or equal to 0. So this is only defined on this one. And this one is defined on the whole line, because before it's becoming undefined, I cut it off. So now what it does is, you come with this path here up to approximately time r half, and then you shift that v in the parameterization somewhat, and then you go over with this beta cutoff to the v. Then, of course, what you forget here is the tail end here, and you have the tail end there. And the minus just takes the u tail end, and minus something like the v tail end. And this is obviously can be reversed. So now is an interesting fact. So for every r, we have an isomorphism. So this total thing here, for every r, is an isomorphism onto a different space. So now let me express r in this way here. You saw this already before, this E1 over T, when I gave this example for this projection which varies dimension. So now, so since this space is isomorphic to this space, then there are subspaces where the plus gluing is 0, and there's an SC subspace where the minus gluing is 0. So we have for every r, we have a decomposition has a decomposition as a kernel of plus r plus the kernel of minus r. So now define a projection pi r from, let's call this E, from E onto this one along this one. So now observe that that's a function of tau here. So I can now look at the following map. Tau u v goes to this pi v. Now these are projections. This is actually retraction. And it's SC smooth. So now you see here, if I just do this operation here as a gluing, that is not an injection because it ignores the tail ends of the functions us and vs. This collects the tail ends. But when do I get uniqueness of this gluing together if I know that this, for example, is 0? The kernel of this is 0. So if I know that this, if I'm knowing here, if u and v are here, then the plus operation is a bijection. So I restrict my plus gluing to this kernel here. And since this is an SC smooth retract, the kernel is actually an M polyfold. So that gives me the local model, what happens nearby here. So now, so the M polyfold would in fact be the kernel, would be all x and y which lie in the kernel of this thing. So now near broken trajectories, I have to extend, I have to choose a filling. Now the complement, so I have to say how I extend. I have to extend in some sense my section to this part here. And the extension to this part, the right extension, is just taking this linear operator. And this, as you see, is an isomorphism if and only if the critical point is non-degenerate. So that would be sort of an example of a filler. Yeah?
You do it in the general case. Are there any obstructions? Or you can always do it.
No, it depends on your model. If you see, you can realize, so your local model is a strong bundle. You could construct a strong bundle where in the fiber you lie in a separable space, and in the top you lie in a non-separable space. Then this would require that a separable complement goes on a non-separable complement. So then you can't do it. So you might have to take some coordinate changes beforehand. You might have to realize your local bundle in the right setup in order to be able to extend it. I mean, but it doesn't really, I mean, it looks like a complicated definition. In principle, of course, it is. But once you compute it, if you do it as a homework, once Moch theory, the features you see there are precisely all over the place. Once you did, you see what is a filler. You know what you have to look for, and you find it immediately. Okay, so now what is Fredholm in the general case? So definition. So then here comes the definition. Then F is Fredholm, provided the first thing is F is regularizing, which means if f of x lies in, then x is in xm plus 1. And secondly, around every smooth x, the germ f of x is conjugated to, let's call it a local G0 of some, to a germ G0 of some KO, abstract bundle. So there's a change, there's a local coordinate description of this germ, which is fillable, which has a filler, which has a filling, which has a filling. So now has a filling, say, G bar 0. So now this is defined on an open set in a partial quadrant, has a filling which is conjugated, so it has a filling so that for has a filling G which is a Fredholm germ. This is already defined what that means. In the case of an open set, I already defined what a Fredholm germ is, which means there's an SC plus section we can subtract from it, and it's conjugated to a contraction to a basic germ. Yeah. So an abstract Fredholm germ is something regularizing. It has a suitable local coordinates description, which has a particular filling, which is actually which is now defined on an open set, which is Fredholm in the sense as I defined before. So it's conjugated to this particularly nice maps after adding some, subtracting some SC plus section. So the result is now the following theorem. So assume the strong bundle F Fredholm section, and assume f of x equal to 0, so that Tf of x0 is onto. So this is actually an SC Fredholm section, is onto, and the kernel of Tf of x0 is in good position to Cx0, here the D before, yeah? So let's the D be gone. To this code, to this sort of the linearization of the code, of the boundary in some sense. Then the solution set near x0 is a manifold with boundary, with corners. In the usual, so I defined what a submanifold is. So it's a submanifold with boundary with corners in particular than the manifold. No, it's actually manifold. Remember, I defined a smooth submanifold which has these properties, like it consists of smooth points. In fact, the solution sets have to be smooth points because it's regularizing. Then the tangent space has finite dimension, is locally constant, and it was sort of the image of this retraction, which is a little bit stronger differentiability property. So that is a strong submanifold in this sense, and it inherits from the polyfold structure a smooth structure. So it's an honest manifold. By the index, yeah. And the index would be then, if you bring it to the normal from the difference of these numbers, little n and cap n.
So after all, that may be called implicit function.
That would be the implicit function theorem. Yeah. So now, I will leave this now, but let me tell you the following, that if F is Fredholm, and you add to this SC plus sections, because you can subtract all these guys, yeah, then it's also Fredholm section. So now if you, and you can so if X is a smooth point and E is a smooth thing in the bundle over E, there's always an SC plus section with this. So you can go in all smooth directions. Now the co-kernels of the Fredholm operator are finite dimensional and SC complement, so they consist of smooth points. So you have enough SC plus sections to fill up a co-kernel. So then this, suppose we have only interior points, then it's easier. Otherwise, you have to say something that you choose the SIs correctly, that you bring this kernel of the things into good position to the boundary and so on. Suppose we have only interior points. You look at all T1 to TL E, Cx, so that f of x plus some Ti Si of x is 0. If you choose you say you do this around the point x0. If you choose the sections correctly, you fill up the co-kernel. It's a manifold by this result, which I proved, M. And then you have a projection onto the parameter space of the T's. Now this is a smooth thing. Take a regular value here, go back, and then this corresponding perturbation is actually a regular perturbation of your F. So that would be some kind of a little version of Sachs theorem applied to this. You could presumably also put some infinite dimensional things here if you make them square summable. I mean, put some conditions on them. You could presumably define a Banach space of such perturbations, which would be sufficiently rich, and so on. And then you could presumably find that Banach space a bare set of perturbations which would have certain properties.
You have a nice representation for the Fredholm maps of index 0, or operators of index 0 here in this.
You mean linear?
Yeah.
So what?
Like something like invertible.
Well, it depends really on your scale structure, yeah? If the scale structure starts with L2 and then you throw in C alpha and then the Bezoff space 1 minus 5 billion with some other, I don't know what the operators are. Yeah? Okay, but now now you see that you have actually a lot of ingredients for doing what you would be doing in nonlinear analysis. You have a Fredholm problem, you have an implicit function theorem, you can talk about Sach, you have a perturbation result. A transversality result, that's a genericity result. So now, And of course, so let me at least, so it covers in particular then just, but you also observe that the formalism looks precisely as before. Yeah? I could call the letters manifolds, bundles. You wouldn't notice any difference to the standard theory. Yeah, the results, the philosophy, everything is pretty much the same. But it covers more general things. So for example, let's take this, let me suppose this is a 2-ball, and then I take the 2-disc. And so this would be in polyfold with boundary. So the open 2-ball, I attach 2 segments, go to the disk. And maybe, oh, let me put a boundary here. Okay, so this is an M polyfold with boundary. So now assume I have a bundle over this. Finite dimensional, and it would jump in the same way. Suppose, which would be covered by this. If I have a Fredholm section, it enforces you actually to jump in the same way because you fill up by an isomorphism. So suppose now I have a bundle over this, finite dimensional, and a section F, which is Fredholm, and the index would be 1. So now I take a SC plus section, take a perturbation, make it generic. You can also, near the boundary, choose the perturbation so that you put it in general position to the boundary, for example, or in good position to the boundary. Then the solution set of this thing would be, say, something like this. So maybe something comes out here, goes there. Another piece would be going like this. And you might have a solution set which looks like this. And there would be a submanifold. So that is. So it behaves very much like the finite dimensional theory, here, as you saw. But you would have to require in finite dimension its Fredholm. And Fredholm would take care of coherent jumps in the bundle and in the base. Yeah.
All connected components have to be in the same dimension, or do you?
No, so the Fredholm index is only locally constant. So now since I say it, yes, on connected components would actually be the same because it's linearized Fredholm. So I think one can show that locally the Fredholm index is constant, of the SC operator is constant. So yeah, so it would be locally the same. On connected components would be the same.
And the perturbation of the index, the continuity of the index is the same kind of result for
Yeah.
this context as
Yeah, so if you have an SC Fredholm, then of course, so what is the linearization if it's not a 0? So the linearization defined here as follows. You take any SC plus section, take a suitable SC plus section, your favorite, so that S of x is equals f of x, and you take f minus s. So then f minus s has a 0 at the point x, and x is assumed to be a smooth point. Then you can linearize this, get from the tangent space into the fiber. And that has an index. And that index doesn't depend on the choice of s because the difference is a compact operator if you take different s. So that has a well-defined index, and that index is locally constant. Yeah.
If you consider the model of polyfold which you wrote before, it was an image of some bundle map. Okay? On one hand. On the other hand, we have another bundle in general, and the problems are in this one equation in this bundle. Yeah.
It is what it is.
So the space where we are solving
It's the solutions. It's actually in a Banach space setting.
yes, it is a bundle space set, yes, is an image of bundle map. Yeah, so on some component it kills part of dimension. Yeah, so therefore dimension can jump down. Yeah.
Well, so yeah, so the model for your bundle is something like this, K, which is a retraction on U and a linear retraction on F.
Yeah.
So it could principally kill independently something on the base and on the top and so on. So it can be completely not correlated.
Yes.
So then when I now say that a section has a filling, it can only have a filling if it actually jumps in a coherent way.
But the problems which are really interested, the origin of the space itself and the problem, the equation, originate from one and the same source. Yeah?
Yes.
Yes, and so this means that the space solution can be more homogeneous and regular than the space where we solve it.
Yes. So yeah. So yes. So the ambient. So in some sense, I would say that the ambient spaces are also quite natural, but they have in general a much wilder behavior than the solution sets of your PDE inside.
Yes.
Yeah. So yeah, and in fact, if you look at this example of the space of broken trajectory, then the broken trajectory. So then remember that I have a projection of this kind, and this is in some sense the gluing parameter. If t is equal 0, I'm in a broken situation. Then in fact, if I'm at the broken situation, that means if r is basically r infinity in this gluing, then you don't do anything. So there isn't the kernel of the negative gluing is actually 0. That means pi 0 is the identity. If I move now in this direction, it becomes non-trivial. So what you have, yes. So and you see if you glue them together, you lose the tail ends. So in some sense, to describe non-broken ones, you need actually less dimensions. So, but on the other hand, the broken one is the boundary. So the boundary looks actually seriously bigger than the interior from a dimensional point of view. Of course, it's all infinite dimensional, but you describe by serious infinite codimensional subspaces the interior, and if you go to the boundary, you describe it by the full space.
Yeah, it may be typical.
That's okay. This is like
Yeah, it's okay, of course, yeah, but it's not so. It's not what you would expect from finite dimensions. You know, then usually the boundary looks lower dimensional.
But I think maybe the proper way to, I don't know, maybe the way I'm trying to grasp this is like in PDEs. If you have a PDE, you try to look for solutions, you try to prove the existence and uniqueness of some solutions. If you build a space, you try to tailor it to the PDE, and it has to be sufficiently big, but where the methods that you employ will work. It cannot be too small because the solution may lie outside of it. So this is what you do here. You try to extend the
Yes,
fluid
so
space. So to
sure. Yes, right. So yes, you just. I mean, the broken things are sort of the bubbles of the unbroken ones. So you add sort of the minimal stuff to it, and then in fact the Fredholm section is just here. That here you apply x dot minus a gradient, and you apply it to this one as well, and it just fits all smoothly together. So there's no so the obvious sections is the one which is defined on this, and that is actually a Fredholm section for the smooth structure you define. So okay, now let me talk a little bit about the categorical picture. And then you see that one only have to understand neighborhoods of an object in some way. And then the general construction of smooth structures for all this kind of problems is to construct neighborhoods of good points. And if you have overlapping constructions in some sense, you have to show that they are sort of smoothly related. So now, in order to, that would be sort of the local theory. And then there's a local theory, because the geometric objects you very often study are maps on manifolds. So you could chop up the manifold into a lot of smaller pieces and make local construction and glue them together. That is what we then call the black box theory, that you do these local constructions with some a priori given set of things you have to satisfy, and then you can just put the things together. So the black box theory would be used to describe local things. Well, that's the So recall that so let me first, so there's something like the polyfold structure for a metrizable space, and then one can define a notion where you replace metrizable space by a category with certain properties where the orbit space is a metrizable, has also topology and is a metrizable space. And the latter has some advantages here if you have to deal with a lot of algebraic structure where you want to say that this algebraic structure in some sense is smooth. So let me do first the following. Okay, so what you want to look at is, and I give you an example, then you see how you have to read things. So okay, so definition. So an EP groupoid. E comes from étale, P from proper, and groupoid is a small category where objects and morphisms form sets. And every element is invertible. Every morphism is invertible. Okay, so EP groupoid is the following. Consists of a groupoid. So a groupoid is a small category with all morphisms invertible. And M polyfold structures on the object set X. Yeah, since it's a small category, it's the object is a set. Polyfold on the object is a set, and the morphism set, say, boldface X. So that all natural maps are SC smooth. So let me write separately what the natural maps are in a groupoid. So in a groupoid, so in a category, first you have two maps, the source and the target. Yeah? So these are the morphisms you can associate to morphism its source and its target. So then S of phi is X, and T of phi, the target, is Y. So these are two of the natural maps. They are assumed to be smooth. Yeah, so both of these things have M polyfold structures. So then, in a groupoid, everything is invertible. So you have this map. This is assumed to be smooth. Then, in a category, you have this map, which associates to a point the one morphism. And then there's another one, namely, you can take the Firebird product. So of all morphisms where the target of this is the source of this, so you can multiply them together. So these are the 5 natural things. So now, when I say smooth, everything is okay except this condition, because you need that the Firebird product has a smooth structure. So why is that? RC smooth, and this all makes sense. It comes from the following. And so I should write this in a different order. And 1, S and T are local SC diffeomorphisms. If S and T are local SC diffeomorphisms, a fiber product can be defined. So this implies that this thing is in a natural way M polyfold. And then, secondly, for every x, in X of every object, there exists an open neighborhood V of X, so that T defined of S inverse V of X closure into X is proper. So see, since S and T are local diffeomorphisms, then above a point could be potentially infinitely many copies of a point. What that says is that locally, if you look at the strata above, it's some kind of a locally finite covering of the stuff below. That is what this says. So this is maybe a complicated notion, but you are actually familiar with this in some way. So let me give you a simple example. Fiber product. Is in a natural way an M polyfold. Has in a natural way an M polyfold structure. So yes, you can interchange because of the property that is invertible here. You can interchange S and T. So now let me give you a simple example. So if you start with a smooth manifold, suppose compact, manifold, take a finite atlas, take a finite smooth covering, finite covering, U lambda. Then you can define, take the disjoint union of this, that's a manifold. And then as a point thing, you take just the collection of lambda x lambda prime, so that x lies in U lambda intersected U lambda prime. That also has a natural manifold. So this is a manifold structure. And then we have obviously an S and a T there, where if you have such an object, you map X into U lambda as a source and as a target into U lambda prime, because it also belongs to this. The local diffeomorphisms. It has all the properties. So in some sense, you can view this. And then, so then obviously we have a natural map from this into M. Then if you divide out by the isomorphisms, you can show that that thing actually has a manifold structure, and it's of course isomorphic to this one. So now, so this is a description of that thing, but actually you would say, well, why do we not just stay with this? But for an analyst, that actually is very useful, because when you do analysis, after writing that, well, this is this differential operator can be viewed as a section of a Banach space bundle of a Banach manifold. And then you start doing analysis, then you wind everything back by going into local coordinates. Yeah, so you could actually now take another description here by just taking an atlas, charts, and taking just here the open sets in Rn as morphisms, the transition maps. And you get also a natural map. So then you have plenty of descriptions of this. And for example, if you take, so now view now M as view M, so M was a manifold, I can do this. So this is some kind of smooth thing. Now associate to M a category. Forget the smooth structure. Every point is an object, and you have only the identity morphisms. Yeah, so I have M now as a category with identimorphisms. Then this here is an equivalence of categories, trivially. So if I would have taken another covering, I get another equivalence. And I want to say, in some sense, they are equal. Now, if you have two coverings, you have a fine refinement of both. So there's an equivalence of, these are equivalents of categories. So in some sense, you would consider them equal. So now you have here an equivalence of categories and here an equivalence of categories. They're actually not onto in general. So now what do you do in category theory? You just say, these are my favorite errors. I want to invert them. And you introduce new maps, which are, so you have a distinguished arrows here called equivalences. And you just say, I view such a thing as a morphism from here to there. But of course, you have to say that different of these diagrams could be equivalent. So there's a notion of equivalence and so on. So I'm not going too far into this. But you can introduce some natural object here, which actually, if you pass to isomorphism classes, gives you a homomorphism. So anyway, so now what we are doing later is, so this was a stupid example, how I have so I have a manifold here. So I've used this as a category, completely algebraic object, but in some sense, that there was a manifold structure told me about the neighborhood of a point describes the neighborhood, which I gather in this way here. So now, in a more general case, I would actually have a category here, and suppose I have some kind of notion what means close by and so on, and I would like to use this to define a smooth structure on that object. And here we were in the situation where we only had a very small set of morphisms, but there's no reason not to assume you have more morphisms from this. So that is the direction in which we are going. So at the moment, I'm describing this kind of picture here. So now, what I want to do is, remember, we had the category of stable maps for Gromov-Witten. Stable maps of Klar. View this as this M here where you forgot all the structure except you view it as a category. The points are the objects and the identities are the morphisms, except that you have here more morphisms. So now this thing has the property that this has a topology, a topological space, actually metrizable space. I never defined this. I just, the quotient divided out by the isomorphisms. So now I want to put a smooth structure on this by constructing such an object X and an equivalence of categories. So an equivalence of categories is something where if you take two objects, the morphisms between them are mapped bijectively to the morphisms between the image objects. And every object here can be reached by starting with a suitable point, going into the set, and then going by an isomorphism to this point. That's an equivalence. So now this thing here, since the quotient set, the quotient thing is a set, you could expect a model which is actually a set, a small category. Yeah? So what I want to construct is, I want to construct a category which is equivalent to the S, but which has all the smooth structures. Now the construction will not be natural, but there's a natural way of constructing things, so that if I construct something else here, I give a recipe. If people follow this recipe, they might end up with different things, but they are sort of equivalent in a very specific way. And this way would be the same, basically, like if I ask Sasha to construct it, he would take, in some sense, in this language here, you would take some open covering. If I ask Joel, he takes another open covering, but then I would know there is a refinement of both coverings which relates the things in some way. So that is, in principle, the picture how you want to define a smooth structure on a category. You want to construct another category which is equivalent, where all the objects, spaces are sets, morphism spaces are sets. You want to put M polyfold structures on them. All the category operations, the natural ones, are smooth. And that should happen since there are choices involved in such a way that two different descriptions can be related. And in the case of a manifold, if I would do it this way, the ambiguity here would be the choice of the open covering. But you could relate two open coverings by taking a common refinement. So this would describe. So for our space of stable maps, I would have to define something, a representation of this category by a small category up to equivalence, where I have these additional smooth structures. So then I can define what a bundle is over such a EP groupoid. It should be a vector bundle. It should be a strong bundle. So a strong bundle over an EP groupoid is of course a strong bundle with a lift of the morphisms. Namely, if below you have X a morphism between Y, and then you have the fibers over this, it's being lifted to a strong bundle isomorphism with a lift. So let me not make that too precise here. So every morphism there has a representation as a linear isomorphism between the corresponding fibers. So then you can say what a section is. A section should be a functor. It should be, of course, here it should be SC smooth. We can talk about SC smoothness. It should preserve, it should be compatible, it should be a functor, it should be compatible with the morphisms. So now, recall that for the stable maps, we have the stable maps, and then we had these things with the 0, 1 forms, yeah? So you want to have this X here, an equivalence. You want to have an E here, which goes into this, so that this whole diagram actually is an equivalence to this category here, to this situation here. Then you had the Cauchy-Riemann operator here, and you want to have a section here representing it. And you want to say that that is Fredholm, provided it has this representation, which is Fredholm, in the sense as I defined it. You can forget the category structure, just view it as going from the object set to the fiber. Fredholm means the germ property locally. Of course, it is a functor here.
What are X and E here?
X and E would be an EP groupoid. And E is a bundle over the object space together with a lift of the morphisms as linear isomorphisms between the fibers. S were the stable maps, and this were the stable maps together with the 0, 1 form. So that's the Cauchy, which I introduced at the very beginning. So with other words, that guy here now is an equivalent formulation of this as far as category theory is concerned. It's equivalence, but it has a smooth structure on it, and the thing is Fredholm. So at this point, I can actually throw the perturbation theory, everything in there, except that there's the issue that I want to make the perturbation theory compatible with the morphisms. Yeah, so I can say that, so the SC plus sections which are used in the perturbation should actually be functors, ideally. So now it turns out that this in general not possible, and you have to break the symmetry to make it transversal, which is not good. But when you break the symmetry, you can keep the collateral damage at a minimum by then taking all kinds of perturbations so that the set of perturbations is invariant under the symmetries. Yeah, so you take a multi-valued functor in some sense. Yeah, so you have a problem with symmetries. Like just take a group action. And then you can show that under any perturbation which preserves a group action, you will never make it transversal at a point. So what you do is you just by brute force take a perturbation, killing the symmetry. Of course, now you killed maybe the counting or a proper counting of your solutions. So just transport the perturbation around with a group action. And you do this everywhere and sum all this stuff up. Yeah? If you do it properly, you get a multi-valued perturbation, which is invariant under the group action. So of course now you have too many things which you count, so you have to introduce rational weights for the things. Now, if you have 500 sections, give every section the weight 1/500. So now if you do this thing at a regular point, which you actually could make regular preserving the perturbation, then under the small perturbation, each perturbation would produce a solution. So there's the change at regular points is not going to change, except at points where you could not a priori make it transversal. And then it turns out in general that you have orientation issues. And if you add up all the situations, the things where you couldn't make it transversal, certain things count like +1, some other like -1. You have to divide by 500. And the local count of solution maybe is 256/500, yeah, at this point. So that means you can only do a theory counting over rational numbers in general. So and that is what's going to happen here. So I'm not going to pursue this further at this point. But you can do now the perturbation theory, which I explained before. You can do this. But then you broke the symmetry. So you have to add up more of these perturbations. Then, of course, in this groupoid, you can show that you can construct local perturbations, sort of with compact support. And then you can transport them in the groupoid around by the morphisms. Because T and S are local isomorphisms, then this here is a local, then if you take this thing here, expression of this kind, you can go from one place to another place. This is a local diffeomorphism between objects, neighborhood of objects. So if you make construction, so suppose two things are related by a morphism above, then you can go from a neighborhood here by this construction. So if you make a little construction like this, you can transport it to all the other points. So that is how a local construction can be distributed over all the groupoid. Then locally you have an automorphism group G. You move this around, then you transport all the other pictures around. So you get several sections. Then if you have another perturbation, instead of, then you take all possible sums you can take for the perturbations. Then you add them up. And so on. Then you can see, doing this, you can construct enough sections compatible with this, so that the set of perturbations is invariant under the symmetries, and you get a high number of problems, all transversal. You just count the solutions of them and take the average by just dividing by your weights. Well, it depends. Locally, usually as many as the order of the group is, of the automorphism group. But then if you make some perturbations somewhere else, then because you have to sort of extend it, move it all over the groupoid, yeah, then you might get some feedback to some situation where you already did something. But in the neighborhood of a point, it's bounded by the order of the group. So now when the solution set is compact, you can cover it by finitely many. So it's in principle the number of things you need times the maximum of things you have to do in a local chart. That's basically the product. No, you have to. It's a power because you take all possible combinations. So so it's some kind of power law of things which, in the worst case, you have to take. Okay, so I think. You see how that in principle would work here. So you have so the situation is so you have a local problem which is not generic. You make it generic by perturbing it, breaking the symmetry. Then you take a finite subset of problems invariant under the local symmetry, and you do this everywhere so that the things fit together in some way. And then you count the solutions of all those things and divide out by how many copies of the problem you had. So take an average. So you break the symmetry, get a family, count everything, divide by the number of copies you had. And that turns out to be an invariant of the solutions, if the index is 0. And the solution set is compact. What does it mean, solution set is compact? It means the quotient dividing out by isomorphisms is a compact subset of that orbit space with a topology. Okay, so now I did overtime as usual. Continues at 2. Black boxes.